Time once again for Astronomy Daily Live. It is 2 hours UTC. Hey, everybody. You can call me Cosmic and welcome, welcome, welcome. Come on in. Come on in. Join the circle of friends gathering together on our virtual porch with our comfy chairs and our drinks and or consumables of choice. I've got the hydrogen hydroxide tonight, going at it. Nice, calming chemical. I dare say the most amazing molecule in the universe. Hey, 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 Bobby Burgess in the house. Hope everything's well with you. Also got a little bit of coffee left in here. I forgot to fill this before I started, so I'm going to finish off the at least the warm part here. Cheers. So I hope everybody's doing well out there. Welcome to everybody who's joining in live, and especially welcome to those who watch this later. I know it's virtually impossible to please and to satisfy everyone. So the choice of this time was, I'll be honest, the most convenient for me. So this is a time of day for me. So now I'm in southeastern Arizona, dark and quiet, right? Dark and quiet. But I'm on Mountain Standard Time in the United States, and that puts me 7 hours behind UTC. So it's 2:02 UTC right now, and that puts it at 7:02 p.m. Um, my local time. And when I started thinking about doing this live stream, um, I I thought of a few things, right? I mean, I definitely wanted to, uh, you know, just share the passion, right? I mean, that's what it's all about. I've been doing astronomy my entire life at every single level, right? I mean, I consider myself a newbie in so many ways um, when it comes to astronomical things. But I'm the amateur at some things, and I'm also the professional at some things. I've I've done it all, and you know, consider myself in a certain way very fortunate to have been able to and continue to have the opportunity to you know do do the kinds of things that I really enjoy, um, and really in a very extreme way, uh, not do those things that I don't enjoy. There's some things that just have to be done, and that's what we call work. Um, but I can happily say that I haven't really done a lot of work in my life because it's all been fun, right? I mean, it's all been uh, pretty much exactly what I've wanted to do, and on top of that, some of those fools actually pay me to do it too. It's actually mind blowing. That somebody will seriously pay me um, to to do exactly the kinds of things that I think are really fun and cool, and I would do it all day, all night. Um, and I have done that, and I will um, continue to do that. Now, being an independent research astronomer is a little tougher. It's sort of like uh, um, running your own business, right? Um, Small business, and so you know uh, the dollars aren't there, but everything else is. Everything else is. And if if I if I have to choose between a lot of what I actually want and a lot of dollars, I will choose a lot of dollars and say, look, as long as I can get my basic bills paid, and when I need a little extra because something breaks, or some kind of a repair or anything else, then um, I should be able to get it, right? But beyond that, I'm I'm not. I don't have any extreme um, interest in stuff, in acquiring things, in having a lot of things. I've got some basic things, but that's it, right? I mean, like telescopes, right? I mean, I built my first telescope when I was 12, and I had that until about a year and a half ago, right? So let's see, that's uh, about 30, 35, 36 years or so. I had one scope that I made, right? Um, and then about a year and a half ago or so, um, uh, did a project that put uh, some extra dollars in my pocket, and it was the kinds of dollars that it's like, what do I want to do with all of this? Because I don't know what to do with all kinds of money. I I just don't have any interest in that, right? But it's like, okay, I've got all this extra. You know what? It'd be really, really nice to have a telescope that would track the sky, right? That I could actually do some science with. And so, you know, I think I dropped. I think this Celestron Nexstar C8. Um, uh, 8SE. I think I dropped like $1,200 for it or so, and it's a good scope. It's a really really good scope. Now it's kind of a downgrade from what I had or have. I have a 10-inch Newtonian, um, uh, but in terms of light gathering capability, that's not a huge difference. So no big deal at all. I already had the CCD camera from another thing that I did uh, many years ago, and I picked that camera up on. I think I picked it up over at Astromart, which I assume is still going on. What Fedora spin do I have on my Linux machine? Right now, I've got Fedora 24. But this weekend, maybe even tomorrow, I'm going to upgrade. I think Fedora 28 is out, so I'm going to jump into the update mode and let this thing update itself to, I guess, what'll be the latest um, Fedora. And I've got another. I've actually got two other Linux machines. Um, the one is also running Fedora. I think it's running Fedora 25. So I might upgrade that one too. And then I have an old machine um, that I got like in 2007, and yes, it's still running. It's still running. Linux still runs. I know that has nothing to do with it, but I've got to put that out there anyway. Um, uh, uh, and you know what? I don't know what that's running because it's been so long. I wanna say maybe it's a version of Red Hat, um, but I don't know. And I don't know if I'll upgrade that or not. Don't know if I've got that or not. I've got um, IRAF on that, which is the image reduction an analysis facility. It's a software suite, the greatest in the world. At, uh, and I say that in a sort of biased way to a certain extent. I know that PyAstro is pretty awesome too, but IRAF I still think is probably the greatest. Um, I haven't played with PyAstro enough to really have an opinion about that. And probably what I should do is I should install PyAstro on one of these two Linux machines and um, give it a run through on the kind of stuff I do, which is um, mostly astrometric, photometric. I could probably get some spectroscopy data somewhere and run it through and see how that does. I like IRAF because I sort of grew up on IRAF, and I worked in the IRAF group. I was a programmer that actually helped develop parts of IRAF. That was holy moly, that was 20 years ago. I worked in the IRAF group from 1998 to 2000, and wow, so that was 20 years ago. I guess I'm getting old. I don't know. How do you measure those kinds of things? Do we measure it by how many times you go around the sun? It's kind of a uh, weird way of measuring time, huh? So Gilles tested Fedora 28 all night. Works great. Very fluid. Very fluid. Okay. So yeah, I'll have to give it a try. I've got a well, I'm embarrassed to say I don't remember what exactly in terms of computing power I have here. I've got a relatively old machine that I sort of use on a regular basis, um, that I inherited um, from a prior job. So that's a pretty old machine. It's probably 10 years old. The newer machine that I also have Linux on is probably just a few years old. Um, and then, as I said, I've got the older one from like, oh man, I want to say like, oh, it's probably 2007 or so. So yeah, uh, well, you know, I'll tell you the truth. I'm just too poor to be able to afford all the latest and greatest things, and I do with what I have. And actually, what I mean, I've got these three Linux machines here, and then I've got a Windows XP machine, which uh, you know I I really like Windows XP. It seems to be very stable and all that. So no problem at all. And Windows XP is actually being run on many um, embedded systems, and probably will be for a long time. I think it's that and Linux um, are mainly um, uh, uh, what are inside of sort of the embedded um, systems. But yeah, so I'm going to take the plunge and upgrade at least one of my machines to Fedora 28. Now, you may be wondering why I'm using Fedora and not any of the other flavors. Um, uh, I've had Linux. I've had a Linux machine since version 0.91. So before there was a version 1 Linux, I mean, I I think the first Linux I got, I actually had to go onto Linus's site um, using Gopher. Do you remember Gopher? And downloaded it there, and um, it was actually Linus Torvaldes's site, and um, uh, yeah, no, I totally agree that Bobby, that I should definitely upgrade. Um, but yeah. Oh yeah, Gopher. Gopher was awesome, wasn't it? Oh man, that I mean that was the most amazing thing I'd ever seen in my life, right? Because you could transfer files. Wow, wow. So yeah. I anyway. So I've had a Linux around for a long time, and I'm pretty sure the first at least one of the first sort of Linux packages was Red Hat. Um, and so I ran Red Hat for quite a long time. I got to say, most of the '90s, maybe into the early aughts, uh, and um, uh, and then I think, I mean, I'd have to go back and actually look, but I think Red Hat either branched over to Fedora or something like that. But you know, um, I'm not too picky when it comes to um, those kinds of things, mainly because I just want a Unix-based um, system. I actually grew up on well, professionally, I use SunOS and Solaris. Um, so I'm definitely a Unix guy, right? And I like the keyboard, and I don't like a lot of help, um, and Unix is very um, hands-on, yet very powerful. And yeah, I think it's still true to say that most of the, at least the professional um, um, astronomical world runs on some kind of Unix, because it's just, I mean, let's face it, it's awesome. It's very awesome. And we always sort of viewed Windows as sort of a thing that we had to put up with, and sort of, a thing that we had to fall back to, as sort of you know uh, a second choice. Um, so yeah, and I mean, I grew up with DOS anyway, and actually pre-DOS. So yeah. Uh, so yeah, when I saw Fedora, I sort of was like, okay, well, that's sort of a cute uh, um, play on Red Hat, right? You know, Fedora, Red Hat. So it's like, okay, I'll start that, and it's completely arbitrary. Um, I've I've seen and used other versions of Linux, and again, for me, as long as I have a terminal that I can write code on, and some relatively decent um, um, graphic type of things, I'm happy. So I've got simple needs in terms of um, computing, and I use computers to compute. I don't um, I don't necessarily use computers to watch TV and um, surf the internet. Now, I mean, of course, I certainly do that, but I mean, if all those um, went away, I probably wouldn't be too hurt at all, as long as I have the computing power, right? You know, to process my data, um, to acquire data, you know, to control instrumentation. Um, I'm pretty happy as far as that goes. So yeah, you know, I should pull over. Uh, I think it's called Pi Astro, and check that out. Yeah. Let's see. Oh yeah. First access to the internet was, I mean, for me, you know, was a 300 baud modem, and um, uh, there was something before Gopher too. Gopher was sort of the first user interface, right? But yeah, there was something prior to Gopher. I know that you could get onto like um, BBSs uh, and all of that, and um, all the alt dot something, you know, all those. Uh, what was those called? I think those still exist too. Yeah, I forget exactly now. But anyway, yeah, I can think a little bit more about astronomical computing, and you know what's being used, you know, to operate telescopes at the observatories. You know what's being used. Actually, the first um, 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 computer I ever used for professional service, for professional work was a it was a mainframe at Stewart Observatory at the University of Arizona, and it was a VAX. It was a VAX of some sort. Um, oh man, I must be getting old. Yeah, use the old um, magnetic tapes. You know those big round magnetic tapes, and um, it had a print terminal, right? And that was sort of root login, right? And then there were terminals. Um, we had a terminal room, which was just outside of the computer room, where there were maybe 8 or so terminals, you know, that you could log in and do your work. And then some people had terminals in their offices, right? Now my group, um, um, which was called um, um, the Speckle Group, we were doing high resolution um, imaging using speckle interferometry. And um, speckle interferometry uses a lot of computing power, a lot of computing time. So in the observatory, we uh, we were despised. We really, honestly, were not liked very much because um, we would slow the system down. You know, we bring it to its knees because we'd be running, you know, something, and you know, I mean, even a VAX, um, uh, um, you know, only has so much computing power, right? I mean, and there's probably more computing power in this smartphone now than that VAX ever had, right? But so we would bring, you know, the system to its knees, and rightly so, people did not like us, right? So we would end up running things at night, instead, when there were less people there. Um, uh, one, because we were getting a lot of complaints, and two, we did want to be courteous and respectful, right? So, we'd run a lot of stuff at night, and you know, at the time, I mean, I was a kid. I basically lived at the observatory, so I mean, yeah, I mean, I never even left for days at a time, right? I mean, I go to classes, then I go to work, right, and then I go to class, go to work, I go to sleep, go out to eat, come back, work some more. Yeah, it was just the typical um, uh, nerdy young scientist kind of a life, and it was fun, and I'm glad all that happened, and I'm glad that it's over, and things really haven't changed all that much, and that sort of gets me back to why I sort of chose this time um, to do this live stream. One, because it's convenient, and for me, um, and two, it's because you know I have such a simple life. I'm sitting here at night anyway, and I'm usually thinking astronomical things. You know, reading articles. Um, you know, thinking about the work I'm doing, whatever else. So it's like, well, why not? Why not just share this around, right? Um, there are lots of people. I mean, I observed that there are lots of people who love astronomy as much as I do, if not more. And so it's like, well, what? Let's get them all in one place. And so I thought of this circle of friends, you know, sort of like a back porch, where we pull up our lounge chairs and our favorite consumables or drinks of any sort, and yeah, shoot the shit about astronomy. So let's do that. Let's do that. Let's do an object of the day. Um, and I'm sort of thinking that I don't think that we've done a Messier object in quite a while. The other day I did a constellation of the day where we randomly chose the constellation Tucana. Um, and I think prior to that, I think I did an NGC object of the day. But let's do a Messier object of the day. So the Messier objects are 110 non-stellar objects, and I'll share my screen here so you don't have to stare at this ugly mug too much. Here we go. Hide that. Yeah, I don't know if there are any more phone BBSs. Wow, do phone modems, is, is that a thing anymore? I don't know. I don't know. Anyway, so the Messier objects are 110 non-stellar objects. So that's anything that's not a star. So, like a galaxy, a globular cluster, an open cluster, a planetary nebulae, and a gaseous nebula. And so Charles Messier he was a comet hunter back in like in the 1750s, and he was looking for comets, and he actually discovered something like 32 or 33 comets, and comet hunters more or less look all over the sky, right, everywhere, and they do this as often as they possibly can, right? I should actually be running my live stream on my smartphone here so I can monitor, make sure that make sure that it's actually running. Come on, there you go. Here we go. Da-da-da, there I am. Okay, good. Um, and you know, so he became like all the other comet hunters of that day, um, extremely extremely familiar with the sky, right? Because I mean, he's looking for moving targets, right? So I mean, he has to be able to, you know, uh, um, come across something that looks like a comet, and then either draw it or somehow remember where it is, and then go back the next day or the next week or the next month, and look again and see if it's moved, right? What he noticed over the course of time is that a number of these objects that he found, which you know I don't know if they just looked fuzzy to him actually because of poor optics or anything else, or if he was a comet hunter looking for fuzzy objects and therefore saw everything as a fuzzy object. Because things like open clusters don't look don't look like fuzzy objects, right? They don't look like comets. But what he did is that he found 110 of these objects that looked like comets but didn't seem to move. And so he wrote down the coordinates of all these objects, um, uh, at least with the personal intention of don't bother with these, right? Because they're not comets, therefore they're not interesting. Well, it turns out that these are, galaxies and clusters and nebulae, which, of course, are extremely interesting, at least, at least as interesting as comets are, right? Not to knock um, comets down, because comets are mind blowing. Um, anyway, there's 110 of them, and actually, once a year, around the vernal equinox, around March 21st or so, you can actually observe. Um, well, some people say that you can see them all, but I'm going to say that you can see all of them but one, and all of them but one in one night, and they call that the Messier Marathon, because you're up all night long, and it's a long night, and you observe 110 of these things, um, and it's fun. It's a challenge, and if you get really good, then you can do what I did, and do like a Messier Plus marathon, where I would clear the sky of Messier objects in 1 or 2 hours, um, and then I would have to wait, you know, several hours, um, for sort of the next set of Messier objects to rise. And so while I was waiting, I would also observe a bunch of um, NGC objects. And so I think one night, a group of us observed something like 240, 250 objects, um, um, one night, and that, yeah, that was just absolutely insane. I think uh, that was like climbing Mount Everest, and it's like once you get once you get to the top of that mountain, it's like, whew, I'm not going to do that again. So yeah, I did the marathon probably, 4 or 5 or 6 times or so. After after that, it sort of, I mean, it's not that it gets boring, or less challenging. It's just, it's sort of like, oh, I've done this enough. Let's do something else. All right, so there's 110 of them. So I'm going to have random.org here choose a random integer between 1 and 110. Now with the Meze objects, I I I can usually remember what they are as soon as I see the number, or at least I think I remember what they are. I think I'm hitting maybe 60% right now. So yeah, let's see what it's going to be tonight, and then we'll sort of uh, investigate this object, whatever it is, a little bit more, and you know we're thinking astronomy, right? So cool. All right, here we go. Drum roll, please. Boing. M108. M108, I'm pretty sure, is a galaxy. Is it a galaxy or a globular cluster? Oh man. See? I think it's a galaxy. I think it's a galaxy, but I don't remember anything about this thing. I don't know where it is. I don't really know what it is. Let's go over to Simbad. Simbad is a great place to find out, just sort of basic information about any object. It doesn't, I mean, and we're talking any star, any galaxy, anything, right? I mean, it doesn't have to be a non stellar object. It can be, anything, right? Um, okay, look, there's a little thing at the top here that says Gaia um, data release 2. For now, Gaia data release 2 data are not in Simbad. Okay. Um, uh, the CDS will perform a cross-identification with Gaia DR2 with the astronomical objects in the Simbad bibliographic database. This will be done with very strict criteria to avoid erroneous cross IDs, especially only the 6.5 million objects with subarc second coordinates. Okay, so expect that to be ready the end of June. That's very cool. So yeah, they're basically going to incorporate. It sounds like a lot of Gaia data release 2 into Simbad. So Simbad is on top of things. I've used Simbad since the early 90s, right? Simbad has been around for a long time, and it's awesome, right? It's really awesome. Um, so let's look for M108, M108, and do a search. Now I think it's a galaxy. I'm pretty sure it's a galaxy. Um, maybe an Ursa Major. I don't know. It is a galaxy. Glad to know that. Yeah, 11 hours. So the celestial coordinates here. This is the right ascension. 11 hours, 11 minutes, 30.967 seconds. And here is declination, plus 55, 40, 26.84 seconds. So I think that's really close to Ursa Major. Um, Uncle Bill, why don't you? Okay, yeah, it is an Ursa Major. Wow, man, I got that. I got that right. I can't believe it. And it's called the Surfboard Galaxy. I've never heard that that name, but yeah, I mean, uh, every there. If you start in like the bowl of the Big Dipper and move south, right? You go from the bowl of the Dipper into Coma Berenices and then into Virgo. That whole area is literally with an 8-inch telescope, right? An 8-inch scope like the one I've got, you've got um, you've got access to at least 100 galaxies, at least, right? Now, if you have like a 16-inch or a 20-inch or larger, it just gets more and more and more. There are literally thousands and thousands and thousands of galaxies in this um, area of the sky. That's why, this time of year right now, early evening, is sort of called, galaxy season, because we're looking uh, we're looking towards the Milky Way's north galactic pole. So we're looking, you know, uh, outside, perpendicular to our galaxy. So there aren't a lot of stars in the way, and there isn't a lot of stuff in the way. And it just so happens that there are, some relatively nearby um, um, clusters of galaxies, which means, the galaxies are pretty bright and pretty big, so we can see them, right? And this is a very very bright galaxy, right? So here are the magnitudes using different filters. So I mean, a filter has a central wavelength, and then it has a band pass, right? A certain width. So um, I d and these are all, defined, right? These are scientifically defined filters that are used, as standards, and depending on basically what wavelength you you look at these objects in, um, they'll appear to be slightly different brightnesses, and that mainly depends on what we call, the color of the object. So, some objects are red, right, and some of them are blue, and some of them are yellow, um, and a a a blue object is going to look very very bright using a blue filter, and is going to look very very faint using like a red um, filter, right? And that's how we sort of get this idea of color, right? So as you can see here, so B is sort of a visible wavelength. Um, you can call that blue if you want. J, H, and K lean more towards the infrared, right? So they're, um, uh, yeah, I mean, very, very, very red, and leaning towards the infrared. U, G, and R are visible wavelength again. U is sort of violet. G, I guess you can call, is green. R is red. I and Z again are the infrared wavelengths. And as you can see, as we move towards the red here, right, it's getting brighter and brighter and brighter. So we could call this in very very general terms sort of a red galaxy. And if you look at the picture over here, and we'll look at this more in just a little while, but you can see that this galaxy is not exactly edge on. It's sort of tilted a little bit, right? It's definitely a spiral, and in fact, it says here that it's a spiral SCD, but it's a very open spiral. So the arms are very very open. Kind of hard to tell here because the angle is such. But look at all that dust. Look at all that crap in there, right? And it's that dust that makes it red, right? There's not a lot of blue, but there's quite a bit of red, right? And don't trust these colors, because these colors are uh, um, uh, what's sort of called false color, right? I mean, designated certain wavelengths to be certain colors, and you know, the colors that we assign to wavelengths are arbitrary, really. Um, you know, there are such things as true color, and that would be, you know, the color that sort of matches our eyes, what our eyes can see. Um, so, uh, but yeah, I mean, it's definitely much more red than blue, right? I mean, it's pretty faint in the blue, and it's pretty bright in the red. So that's pretty cool. Got a bunch of different names, bunch of different names. Now, Pamela Gay, um, and you know, this is one of my gripes, right? I mean, I like Pamela, but she calls these license plate names because, you know, it's you know, 110 um, 837.4 plus 555.624, and I just have a little bit of gripe with that because it seems to sort of you know, um, uh, degrade what what these names are actually designating. And what they designate, um, as you can see, most of these numbers are the same, right? 11085, 1108337, 1108, 110836. Okay. The first set of numbers here is the right ascension, right? So 11 hours, 11.6 minutes in this case, or like 11 hours, 8 minutes, 5 seconds, say. Um, and then the second set of numbers designates um, the declination. So what these names are, right, are the positions of these objects in the sky, right? So it isn't some kind of silly designation, um, you know, almost a meaningless one. It has a lot of purpose and value. So yeah, it's just a gripe that I've got against several astronomers who you know, sort of agree that, you know, these names are silly, um, and it's like, no, 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 these are um, these these are useful pieces of information, right? I mean, really, something like M108 is much more useless, right, than any of these other names, right? Um, Even NGC 3556, if you know um, that the NGC catalog starts at a right ascension of 0 and goes all the way through, you know, to a right ascension of 23 hours, 59 minutes. Just by knowing the NGC number, you can get a really, 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 really general idea about where it is in the sky, right? Uh, but you know, TC 917, it doesn't help me um, in any way to know anything about this object. I'm going to have to dive deeper. But when I get a name like this, right, at least I know exactly where it is in the sky, right? And that's something. Anyway, it's just a gripe, personal gripe. Cheers. So, being a Messier object, it has been studied to death, right? So we'll take a look at a few of these references in a little bit. I like to save that to the last. Oh, let's see. let's look at some measurements and some observing logs here and see what's going on. We've got some distance measurements and some velocity measurements. So let's see how far away we think this galaxy is. There's pretty good agreement there, right? I mean, yeah, by a factor of 2. So that's not too bad. That's not too bad. So what do you say? It looks like the average here is maybe about 10 or so, right? So that's 10 megaparsecs or 10 million parsecs. A parsec is 3.26 light years. So a megaparsec is just a million of those. So I've grabbed my handy dandy calculator, which, as I say, every good scientist, okay, has within his or her reach at any moment a hand calculator. Okay, now you can't cheat and use the calculator on your computer, right? I'm talking about an actual, right, physical object. So every good scientist has one of these within arm's reach. Okay, so 3.26 million parsecs, and we're going to multiply that by 10. Right, so that's an easy multiply. So oh yeah, that's really nearby. 32.6 million light years away. That's backdoor, right? I mean, that's really backdoor. That's or uh, not back door, next door, really next door. Um, yeah, and that makes sense, right? Because I mean, when we look at it, we can see a lot of detail, right? And it's really big and it's really bright. So I mean, you know, the fact those three facts alone tell us that it's really close, right? I mean, it's really nearby. And yeah, I mean, 32.6 million light years might seem like a long way off, but no, that is you know practically next door. Um, so so uh, um, so yeah, that's pretty cool. And the velocity here also is indicative of the distance to a certain extent. I mean, if you buy this idea that the universe is expanding, um, then the fact that it's moving away, excuse me, um, moving away from us at, as far as the galaxy goes, at a pretty low speed, 680, 700 kilometers per second. Um, we are moving away from it, or it is moving away from us. At that is a pretty decent clip, but that's not very fast either. So yeah, that's also indicative of the fact that it's relatively close to us. So that's pretty cool. Let's look at these observing logs here. Um, let's see, are these observing logs or are these observing logs? I don't know. Let's see. Let's display all measurements here and see if there's anything interesting. Oh, we already did that. Okay, are these the observing logs? Didn't I do this? Maybe I did. I'm going to try it one more time. Okay, so it sort of looks like that's it. So let's just look and see what this is. Is this NGC 3556? Is it? Yeah, yeah. Okay, it is. So I don't know what these are going to be. Let's take a look at one. I don't know if that's the way to do it or not, but let's do it anyway. Okay, so this is the Infrared Space Observatory. And it looks like maybe just some photometric measurements at a couple of different wavelengths, very long wavelengths, right? 60 micron and 100 micron. So, this is in the thermal infrared. So they're actually looking at the heat from this thing. And it looks like these units are in Janskis, JY. Is that what that means? I think so. So, interesting enough, these lines here, these are I guess the way that I would interpret this is that this is sort of the band pass, and this is the error in the measurement of the photometry, right? So pretty wide band and relatively, yeah, I mean, a decent sized error there, I guess. Let's see, what else is there? That didn't look too interesting. Let's see if there's another one. Okay, this is sort of the same thing, I think. Yeah, so this is looking at what, 170 microns. Okay. Here's a thing called CAM1. Let's see what that's about. All right, so let's see. Okay, so again, they're looking at this galaxy at 12 microns, right? 12 microns and pretty small field of view, right? So here's 11 hours, 11 minutes, 40 seconds, 35, 30, 25. So what, this is like 15 arc seconds across here and maybe 2 or 3 um, arc minutes. And I shouldn't actually call this arc seconds. There's a translation. One hour of right ascension is actually 15 degrees. So yeah, this is a relatively square uh, area of the sky, maybe 3 arc minutes on each side or so, and so yeah, it looks like they're just looking at the very central region of this. Okay, there it is. Field of view, 3 arc seconds. Thank you. So they're looking at M108 at 12 microns, which is definitely into the thermal infrared as well. And yeah, they're seeing some interesting structure here. Now the resolution, um, isn't 3 arc seconds. No, it should be 3 arc minutes. I don't know. Um, Maybe that's what each pixel is. Yeah, that would make a little bit more sense. But yeah, seeing some interesting structures here. Um, so very, very cool. Very cool. I like to see pictures if I can. Let's see what this is. LWS02. I don't know what that is. Okay, it looks like little spectra of some sort. Oh, I'm being summoned. I'm being summoned to play doorman. So hold on 1 minute. Hold on. He comes up to me uh, and says in kitty talk, he's like, I want out. I want out now. And so I get up and I go to the door and I open the door and I'm like, okay, come on. And he looks at me like, what? What? So, but yeah, he's out now. So, and sorry for the resolution of these things. They're really, really, really small. Nothing much I can do about that. I don't think. It's not much to see here. Yeah, they're looking here between 50 and maybe about 200 microns or so, and I'm not quite sure what that is at all. Not quite sure what that is. As I said, I'm not trying to educate here. We're going along this journey together, right? So there's tons and tons of stuff that I don't know what any of this stuff is. Oh yeah, there's some interesting looks like maybe emission there, right? You see how it goes down and then back up and then back down. So maybe there's some kind of an emission there at 100 microns. Don't know what that represents at all. Let's see. These are saying they're off source, so they're looking at sky. Okay, that's not incredibly interesting either. These look like they're off source as well. So yeah, not quite sure what those are talking about. Um, all right, well let's run through a few of these papers. There's way too many, right? There's way too many. But the cool thing is that these papers they've ordered them uh, in descending date. So from the latest and greatest 2018 backwards. So I like that. I like that idea. So we can start from the latest and greatest and go from there. So Chandra is a X-ray telescope out in orbit. So it looks like Chandra probably looked at this galaxy. Not too surprising at that. Um, Yes, submit to the feline overlords. They, I'm absolutely convinced that cats are an advanced um, um, species. I think that they are at least thousands of years past us. That they've sort of done the human thing and found it found it to be just sort of too much trouble, and um, uh, you know they're really into meditation and just just relaxing, right? Relaxing, sitting back, having a good time, not worrying too much about things, just doing their things. I actually consider them very, very, very advanced. I also think that they have a grasp of gravity that we humans just can't even comprehend, right? I mean, their abilities in terms of jumping and to and from great heights is really in a lot of ways it defies our physical laws. So I think that they actually have the ability to change their local gravitational field, so they can become either lighter or heavier. If you've ever tried to move a cat that doesn't want to move, I don't know if you've noticed this or not, but to but to me, right, they become heavier. They become almost immovable, right? And so the only thing I can think is that they can change sort of their local gravitational field, um, to make them feel heavier to us, so we can't move them, right? Because they don't want to move. Anyway, I'm getting off on weird tangents here. We're talking about M108, Messier 108. Um, uh, um, so Gilles' channel was mentioned on Report of the Week. Very cool. Very, very cool. I don't know anything about Report of the Week, but that sounds pretty important. And over 3,800 watching. Wow. Okay. Well, Gilles, I think that might be an interesting boost for sure, and well deserved. Well deserved. So I mean, what you're doing in terms of you know, talking about radio and talking about computers, man, it's awesome. It's awesome. It's like nothing that I've ever seen, and and so I am so proud of you. It's really really awesome. So uh, hopefully that'll bring in, you know, subscribers, and you know, yeah, you're gonna have to get even more responsible now too, which yeah, you know, I don't know if I can handle that kind of responsibility. Cheers. All right, so let's keep looking at M108, and then I'm going to let you go here a little bit, just looking at some papers that were published that supposedly reference M108. And let's just see if there's anything, you know, I like to look at the titles and see if there's anything that sort of pops out. Um, but I mean, M108 is obviously a very, very well studied object, and will continue, you know, to be um, 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 a well studied object. So yeah, let's just see. Spitzer looked at it, looking at it in the radio, of course. Let's wonder if there are any radio images, radio continuum emission on 35. Let's just look at this one, and because as I said, I mean, oh man, I would love to get into radio astronomy. You know, to not have to worry about daylight and clouds is like a dream come true. I mean, I live in a really dark place, right? I mean, in terms of astronomical perfection, this is this is about as good as it gets, right? But oh man, if I could put radio into that too, woohoo! So changes for radio continuum emission of 35 edge-on galaxies observed with Carl G. Jansky Very Large Array in D configuration, data release 1. So the VLA, I mean, I assume that that is the VLA over in New Mexico. I flew over on the VLA once on my way to Chicago, and never actually been to the VLA, but I definitely uh, saw it. So very very awesome. Let's take a look here at the paper. So Report of the Week has his own shortwave podcast. Huh. He mainly does food reviews. Huh. Yeah, Jill, you might have to be a little responsible. That sucks. I'm sorry. You just you know, you've got to stop being so awesome. That's all. So let's see here. 35 edge on. So hopefully intensity maps. Okay, so we're looking at intensity maps. That's a good sign. I want to see if we're actually looking at M108, which is also NGC 3556, right? Radio continuum in the L and C bands, centered on approximately 1.5 and 6 gigahertz. So wow, that's isn't that like microwave? 35 edge on galaxies have inclinations higher than 75 degrees. Blah 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 blah. Let's get to some pictures here. 5 galaxies with modified distances are those, which does not include M108. Okay, so there are other papers. Of course there are. So yeah, this is more or less just describing the survey that they did. What kind of observations they made, what kind of instrumentation, what the calibrations were, how they reduced the data, how they analyzed the data, et cetera, et cetera. Wow, this is a big, long paper, too. No pictures. Wow. There's probably pictures at the end. Sometimes authors put all the pictures and tables and whatnot at the end. Let's just do a search for 108. Probably going to be listed as an NGC object. Yeah. Okay. So, what was it? 3556? Is that right? Let's go back to Simbad and go up to here. Whoop. Yeah, 3556. 3556. So galaxies with flatter alpha values, not quite sure what an alpha value is, at the centers often have indications of central activity. In some cases, such as NGC 3556 and others, alpha is flatter at the C band than the L band, suggesting a higher contribution from thermal emission at the higher frequency. Okay. So here's a sideways table. So according to this paper, I'm sorry, you're going to have to tilt your head. Yeah, I don't have a way to rotate this. Sorry. Looks like they're saying 14.09 megaparsecs. So I think we computed 10. So they're saying it's a little bit further than that. Anything else here? Doesn't look like there's anything else here. Of course, this is just the RA, the right ascension and declination. So let's keep going here. Okay, so what does this table say? Imaging results C band. Ah. Well, there's lots of numbers there for sure. Let's see if it says anywhere what all these numbers mean. There's a rotate button in the pop-up toolbar at the top of the page. No. Where? This one? Oh, there is. Uncle Bill, what would I do without you? Uh-oh. It's not doing it, though. Okay, hold on. We're going to go back. There we go. Well, yeah. I'm not going to sweat this too much. I want to see what these things mean. Column 1 is galaxy name. Column 2 is some kind of weighting. Rob 0 denotes Briggs weighting with robust value set to 0. I don't know what that means. UV tap refers to the UV tapered version of the former. Columns 3 to 5 synthesize beam parameters. So this is the beam size. Looks like in arc seconds. Come on. How do I get rid of this thing up top? Oh, well. So this is the beam size, probably right ascension and declination. What is with this thing? major axis, minor axis, maybe. Yeah, but it looks like it's in arc seconds. Um, synthesized beam parameters. I am not quite sure what BPA stands for. Column 6 is the L band central frequency in gigahertz. Okay, 1.57 gigs. Um, column 7 is the Stokes 1 RMS noise. Now, the Stokes to me is like a polarization value of some sort. So I don't know if that's what that means or not. Peak intensity. Um, so that's this one. So let's just sort of look. You know, here's some galaxies here. This is obviously brighter than all of these. Let's see what 3556 is. Okay, so 33.87. So yeah, okay. So it's brighter than some and fainter than others. All right. Peak intensity in the case of two values given, the first is the peak intensity of the galaxy, and the second higher value is the peak of the map. Okay. Dynamic range in the image. Column 10 is the Stokes Q and U average RMS noise. Again, I sort of interpret that as some kind of a polarization um, um, thing. But yeah, Uncle Bill saves the day and makes everyone dizzy. That's a ninja for you. Column 11, peak intensity of the polarization map. So yeah, this is probably polarization values there of some sort. Star formation rates. Okay. So I'm sort of interpreting this column as a star formation rate, solar masses per year. So can we find 3556? Yeah, here's 3556. See if I can highlight that. Got to do this with one hand. There we go. So it looks like they're saying that NGC 3556 is making like a little over 2 solar masses per year of stars. Okay. How does that measure up with all the other ones? Again, it looks like maybe it's right in the middle. That's pretty cool though. Flux density. Again, that's I would sort of interpret that as sort of just a measure of brightness. Man, you know what? Look at this. There's no pictures. There's no pictures in this whole thing. It's absolutely useless. All right, well, very cool. I think. Oh, wait a minute. There's some. How did I miss these? Oh, how did I miss these? Wow, look at all these. I don't know how I missed all these pictures. Sorry, I'm making you really, really dizzy because I'm scrolling back really fast. Wow, there's lots of pictures. Okay, I take back everything I just said. Holy moly, there's a lot of pictures. Okay, I see. This is showing different galaxies. Oh, all right. I'm gonna have to let's see if 3556 is in here. There it is. So it looks like this is looking in the C band, the L band. There we go. And these are, yeah, so positive 55 degrees, 36 minutes, 0 seconds. Here's 38, 40, 42, 44. And then going across and right ascension. Let's see. We're talking Oh, it's really hard to see down here. 11 hours, 10 minutes, 24 seconds, something like that. But let's just see what these pictures are showing. Oh, I don't know. Okay, so this is an optical picture and also I guess a C-band picture, polarimetry picture. See these lines here? These show the magnitude and direction of of um, of the polarized light, which is sort of indicative of magnetic fields. So we're actually maybe getting an idea of magnetic fields here too. That's very cool. So A plus B plus C. Um, not quite sure what they're talking about there. Anyway, depending on how you look at these objects, you're going to see different stuff, right? And this is a perfect example of that. But this is all the same object, right? M108 and GC3556, and um, looking at it at a couple of different radio wavelengths, and actually looking at the polarized light also, which is pretty cool. So you can even see maybe there's a spiral structure there of some sort. Very cool. See if there's any other reference to 3556, and then I'm going to let you go because man, we're really running late here. Okay, I think that looped around. So okay, all right. I think for now let's let M108 go. There we go. Pretty cool. Pretty cool. Nice galaxy. Yeah, if you ever get a chance at a telescope to look at um, M108, definitely, um, definitely ask for it. And I don't know if you knew this or not, but if you go to a star party, right, at a relatively dark site, and ask somebody to show you um, M108, um, they'll probably be pretty happy about that because when you go um, to a star party, um, wanting to show people things, what you usually end up doing is showing the moon, showing the planets, and that's very very cool, right? That's very very cool. But what's even more cool, right, is to show um, 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 people things that they would never otherwise see, right? And as the host, or at least one of the hosts, that have a telescope there showing people, it's kind of nice to not have to look at the same thing over and over and over again all night long. So I encourage you, um, when you go to a star party, um, walk up to the astronomer and say, hey, I would really like to look at blah. And, you know, uh, maybe what they'll do, if there's a line, right, and everybody wants to see Saturn, right, maybe they'll say, hey, why don't you check back in a little bit when there's not a line, and we'll go look at a whole bunch of stuff. I mean, I've done that. I will continue doing that. I don't, I, I like to show people as many things as I possibly can. So yeah, if you have a scope, or if you get a chance, to look through a scope, ask the operator, to look at something else, right? One of the Messier objects. Um, and M108 is pretty cool. Is you can definitely tell that it's elongated, and it's big. It's really really big. And as um, um, Uncle Bill pointed out earlier, it's right next door to a planetary nebula that's called M97, also known as the Owl Nebula. So while you're in the vicinity of M108, why don't you ask that same astronomer if they can move over to M97, and they'll be happy to show you that, because that is very, very cool to see. So, all right, I think I'm going to get out of here for tonight. It's wow, is it really 3:25 UTC? Wow. Okay, we're going to get out of here for now. Yeah, it's been ringing in my ear for quite a while. I gotta get back up to the mothership for sure. And look, I'm out. I'm out of fuel. So yeah, I've got to refuel and take care. Have a great evening, a great night. Smash the thumbs up, thumbs down, whatever, right? Um, Leave a comment, subscribe if you haven't already. Share this around too. You know, if you know people who have any kind of a um, 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 interest in astronomy, and don't necessarily want to be just sort of lectured to and talked at, and all that, bring them in, right? Invite them in, um, and see if they like this kind of a format, and where it's casual, it's fun. Um, I learn a lot. I learn a lot, right? Um, Hope you do too. But yeah, this is just a thing about sharing the passion. That's it. That's it. I'm not really trying to communicate. I'm not really trying to inspire, um, or anything at all. I love this stuff, and I mean I can talk about this all day and all night, and given the chance, I do. So this is my opportunity to do that. But I also respect your time. I don't want to keep you here too long because I'm doing this every day. So if you miss it today, you can pick it up tomorrow or the next day or the next week. Um, Come on in anytime. You are all extremely welcome. And with that, I'm going to get out of here. Peace, cheers, and all that. I will see you on the spin like 20, 22 and a half hours from now. All right. Take care, everybody. I'll see you tomorrow. Bye.